Let's start Chapter 9, Duality in Splitting Methods. In this chapter, we present Attouch-Thera duality, which is a duality framework for monotone inclusion problems, which is analogous to but simpler than convex duality. Convex duality has several distinct and complementary interpretations, and Attouch-Thera duality takes one of them and generalizes it to operators. We then discuss the intimate connection of Attouch-Thera duality with the base splitting methods that we had studied in Chapter 2. The outline of this chapter is as follows. First, we will review Fenchel duality, then we'll present Attouch-Thera duality, and then we'll explore the connection of Attouch-Thera duality with the base splitting methods. In Fenchel duality, the primal optimization problem is of this form. Minimize f of x plus g of x, and as always, we assume f and g are CCP functions. The corresponding dual optimization problem is to maximize minus f star, composed with minus u, minus g star, evaluated at u. This primal dual problems pair is generated by this Lagrangian. The issue of total duality is a subtle matter, as it is always the case with convex duality. Here's one interpretation of Fenchel duality. For the sake of simplicity, let's assume that total duality holds, and furthermore, let's assume that the functions f, g, f star, and g star are all differentiable. The primal problem, which is originally proposed as minimizing f of x plus g of x, can be reinterpreted to the problem of finding a point x such that grad f and grad g evaluated at point x sum to be equal to 0. In other words, we can reinterpret the primal problem as finding a point x such that grad f evaluated at x and grad g evaluated at x, they sum to be equal to 0. The dual problem, which is originally posed as maximize u of minus f star evaluated at minus u minus g star u, well, we can now reinterpret this problem as finding a u such that grad f of star evaluated at u plus minus g star evaluated at u is equal to 0, which is equivalent to finding a u such that grad f star at u minus u is equal to minus grad f star minus evaluated at u grad g star evaluated at u. And finally, since f star is the convex conjugate of the function f, grad f star, that's equivalent to grad f inverse, and grad g star, that's equivalent to grad g inverse, so we can reinterpret the dual problem as this problem, where we find a u such that grad f inverse applied to minus u is equal to grad g inverse is applied to u. The interpretation of this problem is that we are trying to find a gradient u such that grad f produces minus u and grad g produces plus u when the two gradients are evaluated at a single point. So again, the primal problem is looking for the primal point x such that the gradients sum to be equal to 0, and the dual problem is looking for the gradient u such that minus u and plus u are produced at the same point when they're evaluated at grad f and grad g. The subject of convex duality is complex and multifaceted. This is one of the many viewpoints of convex duality. Next, let's talk about Attouch-Thera duality. In Attouch-Thera duality, we consider the maximal monotone inclusion problem, where we find x such that x is a 0 of the sum of the two operators a plus b, where a and b are assumed to be individually maximal monotone operators. For our discussion of Attouch-Thera duality, we will introduce this new notation. I'll read this as A inverse OV because this is the V symbol circled within an O. So A inverse OV can also be defined as A inverse OV is minus identity composed with A inverse composed with minus identity. So the operator A is maximal monotone if and only if A inverse is maximal monotone, and A inverse is maximal monotone if and only if A inverse OV, which is the A inverse under this congruence transformation, is maximal monotone. So A inverse OV is maximal monotone if and only if A is maximal monotone. The Attouch-Thera dual monotone inclusion problem finds a u that is a zero of the sum of these two maximal monotone operators. The first operator is A inverse OV, and the second operator is B inverse. Attouch-Thera duality is, in a sense, easier than Fenchel duality because the primal monotone inclusion problem, finding a zero of A plus B, has a solution if and only if the dual inclusion problem, A inverse OV, finding a zero of A inverse OV plus B inverse, has a solution. So a primal solution exists if and only if a dual solution exists. Let's prove this. So this condition, there exists an X such that 0 is within A plus B evaluated at X. This condition is equivalent to a primal solution existing. Well, this is equivalent to saying that there exists an X and a U such that AX outputs minus U and BX outputs plus U, and minus U and plus U, of course, adds up to be equal to 0. Then this is equivalent to saying, to taking this minus U is in A evaluated at X. We multiply by minus 1 on both sides. We apply the A inverse on both sides, and then we multiply minus 1 on both sides to get this inclusion. And for this inclusion with B, we just apply the B inverse on both sides to get this inclusion. So here we have equivalence. And finally, well, since the output of AOV is minus X and the output of B inverse is plus X, they add up to 0. So this is equivalent to saying that there exists a U such that Z0 is an output of AOV inverse, A inverse OV plus B inverse evaluated at U. So that completes the proof that a primal solution exists if and only if a dual solution exists. When it comes to Attouch-Thera duality, there's no notion of strong duality because there is no notion of function values. Note that when A is equal to partial F and B is equal to partial G, then Attouch-Thera duality is roughly similar to Fenchel duality. So Attouch-Thera duality generalizes Fenchel duality in the sense that the class of subdifferentials of proper convex functions, CCP functions, is a strict subset of monotone operators. So the type of duality that you can express is in some sense broader when you're considering the general class of monotone operators, and hence when you consider the general class of Attouch-Thera dual problem pairs. However, Attouch-Thera duality does fail. It fails to capture the subtleties of Fenchel duality, and therefore it is not a generalization in that sense. In Fenchel duality, strong duality may fail. A primal solution may exist while a dual solution does not, and a dual solution may exist while a primal solution does not. These type of pathologies do not arise in Attouch-Thera duality. In Attouch-Thera duality, there are only two possible scenarios. First of all, there's, again, no notion of strong duality. So the scenario 1, a primal solution exists and a dual solution also exists. Scenario number 2, a primal solution does not exist and a dual solution also does not exist. Those are the only two scenarios in Attouch-Thera duality. So the subtle pathologies that can make the study of Fenchel duality somewhat tricky and difficult, those do not arise in Attouch-Thera duality. Why do we care about dual solutions? Well, dual solutions, one use of them is they serve as certificates. So when you have an iterative method solving a monotone inclusion problem, it is desirable for the method to produce both primal and dual solutions in the end, as dual solutions can certify the correctness of a primal solution. So if an algorithm returns a primal dual solution, x star comma u star, for the monotone inclusion problem of finding a 0 of a plus b, well, if what that means, when x star and u star is a primal dual solution, what that means is there exists a minus u is an output of the operator a evaluated at x, and minus u star and plus u star is an output of b evaluated at x star. So if such a primal dual solution is provided, then we can verify this condition 1 and thereby certify the correctness of the solutions. However, in contrast, imagine only a primal solution x star is provided. Then, in order for one to verify that the purported solution x star is a solution, then one must verify that 0 is contained in the output of A evaluated at x star plus B evaluated at x star. Well, in general, how does one compute the Minkowski sum AX star plus BX star? In some cases, it may be straightforward to carry out the Minkowski sum and then verify whether 0 is contained within the sum. But in general, this may not be an easy task. So if we have a dual solution provided together with a primal solution, then it becomes much easier to certify correctness of the primal solution. Finally, let's move on to duality in splitting methods. The fixed point iteration with forward-backward splitting, which can be expressed in this way, is often not considered a primal dual method. However, we can make it primal dual by explicitly defining dual iterates as follows. So we first, starting at the iterate xk, we take the forward step to obtain the iterate xk plus 1/2. Then we record the evaluation, the negative evaluation of the single-valued operator A at xk. We record that as uk plus 1/2. And then we take the backward step, so we evaluate the resolvent with respect to alpha b at xk plus 1/2 and record that as our next iterate xk plus 1. But at the same time, we take the differences of the input of the resolvent and then the output of the resolvents and scale it by 1 over alpha and record that as uk plus 1. Note that due to the definition of the resolvent, uk plus 1 is actually an output of the operator b evaluated at xk plus 1. If the conditions are met such that forward-backward splitting converges, so if xk converges to a primal solution x star, then the dual iterates uk plus 1/2 converges to u star, and uk plus 1 converges to u star, the same limit where u star is a dual solution of the Attouch-Thera dual. Using the Attouch-Thera dual, we can characterize the fixed points of Piesman-Rackford splitting and Douglas-Rackford splitting. Here is the characterization. So the fixed points of the PRS operator, which is equivalent to the fixed points of the DRS operator, is a subset of the set of primal solutions plus alpha times the set of dual solutions. Let's prove this inclusion. So let's start with a z that is a fixed point of the PRS operator. Well, if we just write out the PRS operator, that is equivalent to just this thing. So this is the PRS operator, and we're saying that z is a fixed point. And let's just write x as the output of the resolvent with respect to b evaluated at the fixed point. Well, this means that, so this condition, it means that I plus alpha b, x contains a z. So let's write that out explicitly. So we'll write u as the explicit output of the operator b evaluated at x. So then we'll write a z is x plus a u. And then what we will do is we will go to the prior line. We'll cancel out z on both sides. We'll cancel out the factor 2. And then we'll plug in j alpha b z, that's just x. J alpha b z, that's 2x. And then here is minus I. Well, that's minus z. So we plug in x plus alpha u, and we get x minus alpha u. Okay, then here we have a resolvent evaluation. So then what this means, what this corresponds to x minus alpha u is contained in I plus alpha a evaluated at x. So we'll take the operator evaluation of A, we'll make the evaluation point, the output explicitly V, and we'll write the inclusion as an equality in this way. So now V is in AX, and then U is in BX, and then Z is X plus alpha U. Then, well, from this equation, we can simply cancel out X on both sides. We can divide by alpha on both sides. And that tells us that, well, V is equal to minus U, so there's no longer for us, no need for us to keep around the variable V anymore. So we plug in v is equal to minus u. That tells us that minus u is in ax, plus u is in bx, and the z is x plus alpha u. So we'll just keep this around. Z is x plus alpha u over here. Okay, and then we'll just simply repeat this condition in a more symmetric way. We'll also express this exact same condition using the operators that appear in the Attouch-Thera dual. So minus u is in ax. That's equivalent to minus x is in the output of a minus ov evaluated at u. This condition is equivalent to this condition, and this condition is repeated here. So these conditions are redundant, but it's okay for us to say the same thing twice. U is in bx, so u is in bx, and then that's equivalent to x is in b inverse evaluated at u. Okay, and finally we have the forward implication. So this condition implies that 0 is in a plus b evaluated at x. These two conditions to combine, that implies that 0 is in a inverse ov plus b inverse evaluated at u, where z is x plus alpha u. So this last step is an equivalence. So what we have proved is that if we start with a fixed point, an element of this set, then this fixed point z necessarily can be decomposed as a primal solution plus alpha times a dual solution. So hence the fixed point set z is contained in the primal solution plus alpha times the set of dual solutions. The issue of why we only have a forward implication and why we do not have the reverse implication is a subtle one, but let me explain. So if we start from these two conditions, and if we try to imply these conditions, then in general we do not have that implication, because here what this means is that there exists an output of a and b such that they sum to be equal to 0, and we can call that the dual solution corresponding to x, but that dual solution may not be the same dual solution as u. Also here, u is a dual solution, and there is an output of the operators a inverse ov and the a b inverse, that sum to be equal to 0, and that would be the primal solution corresponding to this dual solution, but that primal solution need not be the same as x. So here, if we try to take the reverse implication, then we would have to split into the two pairs of x's and u's, so the pair of x and u that goes into here, and the pair of x and u that goes into here, those two pairs may have to be distinct in general. So hence we do not have the reverse implication in general. The fixed point iteration with DRS in its original form is not explicitly primal dual, but we can make it explicitly primal dual. So here, this is the first step of DRS where we define xk plus 1. Here, this is the second step of DRS where we define xk plus 1, and here is the third step of DRS where we define zk plus 1, the subsequent iterates. In between these main DRS iterates, we can define this uk plus 1/2 iterate, where we take the difference between the input of the resolvent with respect to b and the output of the resolvent with respect to b, and we scale by 1 over alpha. And then here we define uk plus 1 with this combination scaled by 1 over alpha. And if you pay attention a little bit, then uk plus 1, due to the definition of the resolvent with respect to b, uk plus 1 is an output of the operator b evaluated at xk plus 1/2. And if you reason in the same way, but you do a few more calculations, you can conclude that minus uk plus 1 is an output of the operator a evaluated at xk plus 1. So DRS converges under the condition that the maximal mountain operators a plus b, the sum has a 0. So under that condition, then the main iterate zk converges to a fixed point, and under that condition, the primal iterates converge to the same limit x star, and x star is a primal solution. And by the same line of reasoning, we can show that the dual iterates uk plus 1/2, uk plus 1 converges to the same limit, and the limit is a dual solution. And finally, we can show that the limit of zk, the limit of the main iterates, is the primal solution x star plus alpha times the dual solution u star. DRS also has a very interesting self-dual property. So Peaceman-Radford splitting and Douglas-Radford splitting are self-dual in the precise sense that the operators resolvent of A composed with reflective resolvent of A and the composed with the reflective resolvent of B is the identical operator as the reflective resolvent of A minus OV and composed with the reflective resolvent of B minus 1. Well, this identity can be shown in a rather straightforward manner. So if we take the resolvent of A minus inverse minus OV, well, we have something that resembles the inverse resolvent identity, and we can show something like this. So using this identity, and then also using this identity. So this second identity is just the familiar inverse resolvent identity. This first one is not exactly that, but it's very similar. The proof of it follows from essentially the same line of reasoning as the proof of the inverse resolvent identity. So we take the reflected, we take this second composition of reflected resolvents and write it out in this way. And then we make the substitutions. So JB inverse is I minus JB, and then A inverse OV, that's I plus JA composed with minus I. So we just write it out in this way. Then we perform the compositions, we perform some calculations and arrive at the regular PRS operator with respect to the operators A and B. So using the self-dual property of DRS, and if we set the scaling factor alpha to be equal to 1, we can express DRS in this much more symmetric way. So again, we apply the resolvent with respect to B to the main iterate zk to obtain xk plus 1/2. And then we perform the reflection operation, apply the resolvent with respect to A to obtain xk plus 1. And then we obtain the zk plus 1 update by performing the vector sum. So zk plus zk plus 1 minus zk plus xk plus 1 minus xk plus 1/2. But we can insert in between the UK iterates. So this is the same UK iterate. It's the same when alpha is equal to 1. But we can write UK plus 1/2 as the resolvent with respect to B inverse applied to the main iterate zk. And since in this case alpha is just equal to 1, we can also express it in this way. And the UK plus 1 iterate can also be expressed in this way, where we perform a reflection with respect to the dual iterates, the dual UK plus 1/2 iterate, and we apply the resolvent with respect to A inverse OV. And finally, the zk plus 1 update can also be expressed using the dual iterates as well. So we can compute zk plus 1 as zk plus UK plus 1 minus UK plus 1/2. And this form of DRS really nicely reveals the symmetry. It really nicely reveals the self-dual property. Of course, algorithmically, there is no need to use both the x and u variables. The DRS algorithm, which was originally expressed in 3 lines, is now expressed in 5 lines, so it's in a sense more complicated. But what we're trying to show with this expression is that DRS is perfectly self-dual, and we can equivalently carry out the DRS operation, the DRS iteration, by instead considering the UK variables. So if we choose to use compute UK plus 1/2, UK plus 1, and use this iterate, then we can carry out the exact same, the identical DRS iteration in the dual space. So by the way, this self-dual property explains why it is that the infimo post-composition technique and the dualization technique resulted in the same form of ADMM when we derived the ADMM algorithm in 2 different ways in Chapter 3. Finally, let's talk about the DYS splitting method. So let's consider the monotone inclusion problem of finding a 0 of the operator A plus B plus C, where A, B, C are individually maximal monotone operators, and we assume C is a single valued operator. The Attouch-Thera dual of this primal monotone inclusion problem is of this form. So we have the familiar V inverse, we have the familiar minus OV, but we first compute A plus B, C, so A plus C, and so we take the So we compute A plus C and then take the minus OV in forming the Attouch-Thera dual. The fixed points of DYS can be characterized with an analogous line of reasoning. So the fixed points consist of points that are a sum of the primal solution plus alpha times the set of dual solutions. And as with DRS, we can make the fixed point iterates with DYS more explicitly primal dual as well. So again, this is the update for xk plus 1 half. This is the update for xk plus 1, and this is the zk plus 1 update. And in between them, we can insert the uk plus 1 half, uk plus 1 updates. And now if you spend a few moments to think about it, uk plus 1 half is an output of the operator b evaluated at xk plus 1 half. Minus uk plus 1 is an output of the operators a plus c, a evaluated at xk plus 1 and c evaluated at xk plus 1 half. And if the conditions are met such that the main iterate, the zk iterate, converges to a fixed point z star, then the xkx iterates converges to the same limit x star, and x star is the primal solution. The dual iterates converge to the same limit u star, and u star is a dual solution, and the limit of the zk iterate is x star plus alpha times u star. So FBS, DRS, DYS can all be made explicitly primal dual methods in the sense that the algorithms produce iterates that converge. If the main iteration converges, the primal and the dual iterates converge to primal and dual solutions. The DYS splitting method, unlike the DRS splitting method, is not self-dual because the DYS splitting method utilizes the evaluation of the operator, the single-valued operator C, and that is an inherently primal operation, so it's not possible to formulate a self-dual structure of the DYS splitting method.